Assalamu alaikum wa rahmatullahi wa barakatuh. We're going to start with the second part of mechanical oscillations, and this is the first video. At the end of this lesson, you are going to be able to explain free undamped oscillations of a vertical elastic pendulum, a torsion pendulum, a compound pendulum, and a simple pendulum. Finally, you are going to be able to explain free damped oscillations and analyze the graphs of its energies. In this video, we are going to explain free undamped oscillations of a vertical elastic pendulum. Let's remember first that we have mentioned in the first part of mechanical oscillations that an oscillation is characterized by its period, frequency, and amplitude. The differential equation of a simple harmonic motion is x double prime plus k over mx equals to 0. The time equation is x equals xm sine or cosine omega 0 t plus phi, and the proper angular frequency omega 0 is equal to the radical k over m, where the proper period t0 is equal to 2 pi radical m over k. To start explaining the vertical elastic pendulum, we are going first to consider an oscillator formed of a spring of negligible mass and natural length L0, suspended from a fixed point A, while its other end carries a particle S of mass m. When S is attached, the spring is stretched by delta L. The spring with the mass will attain equilibrium at point that we're going to name it O. It's clear that, unlike the horizontal elastic pendulum, in this vertical elastic pendulum at equilibrium, the tension force exists. We aim to start the study from equilibrium position and find the elongation of the spring delta L at this position. As usual, first we should define the system, which is solid S. What are the external forces acting on it? We have weight, mg, which is vertically downward, tension of the spring, which is upward since it's a restoring force. At equilibrium, we can start with sum of forces equals to 0. Thus, mg vector plus t vector equals to 0. We project along x-axis, which is oriented positively downward. Then we have plus mg minus tension equals to 0, while the tension is k times delta L0. Finally, we can find that delta L0 equals to mg over k, where mg in Newton, k Newton per meter, and delta L0 in meters. After that, we are going to find the expression of the elastic potential energy. So, we shift S vertically and release it. The spring then oscillates. Note that the direction of the axis of motion is very important in determining the expressions of the gravitational and elastic potential energy. So, consider x prime or x-axis vertically downward as it's taken before, and the horizontal plane passing through the center of mass G of the solid at equilibrium as the reference level of the gravitational potential energy. Now, to find the expression of the elastic potential energy, we should ask a question. Will the expression of the elastic potential energy vary whether this particle S is above or below the equilibrium position? Let's start at equilibrium. At equilibrium, delta L0 equals to L at equilibrium minus L0. Then, the elastic potential energy is expressed as half k delta L0 squared. Then it is not 0 at O. Now, what if S lies between the two extreme positions, plus xm and minus xm? In this case, choose the first position where S is below O, then in this case X is positive. In this case, delta L can be written as L minus L0, but L is L at equilibrium plus the absolute of X minus L0, then L equilibrium minus L0 expresses delta L0, and we can write it as delta L0 plus X. If S is above O, then X is negative. Delta L, which is L minus L0, equals to L equilibrium minus the absolute of X minus L0. Then L equilibrium minus L0 expresses delta L0, and the answer is delta L0 plus X. So in both cases, whether the position of S is above or below the equilibrium position, then the expression of the elastic potential energy is half K delta L squared, where delta L is delta L0 plus X, all of it squared, where the elastic potential energy is in joules, K in Newton per meters, X and delta L0 in meters. What about the gravitational potential energy? We should know that the center of mass G of the solid at equilibrium coincides with the origin O of the axis of motion. Then the gravitational potential energy is 0 at O. Unlike the horizontal elastic pendulum, the gravitational potential energy plays a role in the oscillations of this pendulum. If at a time t, S is below the reference level, then the gravitational potential energy is minus mgh, which is minus mg, the absolute of X, which is also minus mgx since X is positive. But if S is above the reference level, then the gravitational potential energy is plus mgh, which is plus mg, the absolute of X. Because X is negative, then the expression is minus mgx, where negative X gives positive answer. It's clear that this formula is still valid when S is on the reference level where X equals to H equals to 0. Then the expression of the gravitational potential energy can be minus mgx, whatever the abscissa X, positive, negative, or 0. Keep in your mind that the gravitational potential energy is in joules, the mass in kilograms, and X in meters. Finally, what is the expression of the mechanical energy at any instant? Before we answer, please keep in your mind that at any time t, the abscissa of the center of mass G is the algebraic measure x, and its velocity is an algebraic measure v, which is dx by dt. Now, the mechanical energy is written as kinetic energy, half mv squared, plus the gravitational potential energy, which is minus mgx, plus the elastic potential energy, which is half k into x plus delta L0 squared. You should practice all these steps by yourselves in order to find the expression of the mechanical energy at any instant t. We said before now that if we want to study the motion of any oscillator, we should find the differential equation, then its solution. Now we're going to start with the first method in order to find the differential equation, which is the method of mechanical energy. We said that the mechanical energy at any instant is half mv squared minus mgx plus half k into x plus delta L0, all of it squared. Then we know that we are dealing with the undamped oscillation, so there is no non-conservative forces. What does that mean? It means that the mechanical energy is constant, which is conserved, and its derivative is 0. Then try to make its derivative and check your answers with what I'm going to show you. Use these notes whenever you need. Then, good. The answer is mvv prime minus mgx prime plus k into x plus delta L0 times x prime, with delta L0 equals to mg over k as it was found. Replace it in the equation and we will get finally mvx double prime minus mgx prime plus kx x prime plus mg x prime. Then minus mgx prime plus mgx prime gives 0. The answer is mx double prime plus kx equals to 0, where v equals to x prime, not equals to 0. The last answer is x double prime plus k over mx equals to 0, and this is the second order differential equation without a second member at x. Now, what is the second method? It is Newton's second law. And as usual, whenever we want to use a Newton's second law, we should define the system. And here it is, a solid S. The external forces acting on S are its weight, mg, and the tension T, where friction is neglected. So according to Newton's second law, we have sum of forces equals to ma vector. Then we write mg vector plus tension T vector equals to ma vector. Projecting it along I and writing the tension by its expression minus k into x plus delta L0, then we can find that mg minus k into x plus delta L0 equals to ma. Then we expand k into x plus delta L0 and replace delta L0 by mg over k. After some calculations, we can find that minus kx equals to ma, which is x double prime. Then we can write it as x double prime plus k over m, x equals to 0, and also this is the second order differential equation without a second member at x. Since this differential equation is of the form x double prime plus omega 0 squared x equals to 0, then this motion is a simple harmonic and it has a solution x equals to a sine omega 0 t plus phi, or x equals to a cosine omega 0 t plus phi, where a omega 0 phi and phi are constants and xm is the absolute of a, always positive. The characteristics of this equation are the proper angular frequency omega 0, which is radical k over m, the proper period, and the proper frequency. We're going to solve this direct application on this video. I want you to read the question very well and try to solve it by yourselves. Here we have a vertical elastic pendulum which is shifted by 10 centimeters, and this spring has a stiffness k equals to 20 newtons per meter, where delta L0 equals to 5 centimeters. The question is, write at an instant t the expression of the mechanical energy of the system as a function of m, k, x, and v. So we start with mechanical energy equals to the kinetic plus elastic plus gravitational, and write its expressions: half mv squared minus mgx plus half k into x plus delta L0 squared. Determine at equilibrium the elongation of the spring. Deduce the value of the mass m. So the same steps that we have mentioned in the video, starting with indicating the system, the forces. Then at equilibrium we have mg vector plus t vector equals to 0 vector. After projecting along x-axis, we have finally delta L0 equals to mg over k. So we just replace delta L0, k, and g by their values, then the mass will be 0.1 kilograms. Establish the differential equation in x which governs the motion of s. So we have the expression of the mechanical energy at any instant, we make the derivative because the mechanical energy is constant, so it will be 0. Finally, the answer is yes, it is x double prime plus k over mx equals to 0. This is enough for today. Please copy these notes and study them well. Thank you for watching.